Thank you. I'd first like to thank the organizers for including me in this conference and giving me a chance to speak. I'd like to tell you about some work that I've been doing together with Andrew Cross and Ke Li, also both of them at IBM, trying to understand questions around additivity in both classical and quantum information theory. Okay, so what I'm interested in is, what information theory is interested in is really quantifying the optimal performance of protocols for transmitting, storing, or processing information and data. So for example, we may be interested in understanding the optimal rates of entanglement distillation or quantum key distribution, or understanding the best performance you could get with quantum repeaters, or just transmitting quantum states from one place to another. And in all of these cases, the answers that we get for optimal rates are typically in terms of entropies. In information theory, your answers come as generally linear combinations of entropies. So just as a reminder, the entropy of a random variable is just this sum of minus p log p's, and the entropy, or von Neumann entropy of a quantum state is just given by minus trace rho log rho. And as I said, most of the answers that we have are in terms of these entropies. So for example, if you're interested in compression, the entropy of your source tells you the optimal compression rate. Similarly, in the quantum setting, Schumacher compression can get you down to the entropy in your state, but no further. And the classical channel capacity is just given by this maximum of mutual information between sender and receiver, where the mutual information just quantifies the amount of correlation between input and output of your channel, again, in terms of these entropies. For a quantum communication, something called the coherent information is an achievable rate. And when you're doing QKD, the private capacity is an important quantity that tells you the best key rates that you can get. And it's related to something called the private information, which is just this maximum difference of these mutual informations. And a key property of entropies that we often use is strong subadditivity. It's the positivity of the conditional mutual information that's just expressed by this sum of 4 terms. Okay, so this talk is about additivity, which is the property that, let's say I have some channel, maybe it's quantum, maybe it's classical, and I want to know, I want to evaluate some function on the channel, perhaps a capacity. We say the function is additive if, when I take the channel together with the second channel, so here a blue wire and a gray wire, if the value of the function of that joint channel is just the sum of the individual values of the functions. So the capacity of my blue wire and my gray wire used together is just the sum of the individual capacities of the blue and gray wires. And this is a property that is satisfied by the classical capacity of a classical channel. And it's a property that really makes it possible for us to compute answers in information theory. Especially in the quantum case, non-additivity is the rule. Rather than these 2 nicely coiled wires, you often end up in situations like this guy here. And it's a blessing in some sense because it means we get better rates for classical communication, say by using entangled signal states, or for quantum communication by using degenerate quantum codes. But it's also a curse because for the most part, we don't have simple ways to compute the optimal performance of the protocols that we're interested in. We don't have ways to calculate capacities of quantum channels or distillable entanglements of states or the amount of key you can extract from a given distribution. We just have upper and lower bounds, and in general, these are quite far apart. Okay, what I want to do is talk about a specific kind of question related to additivity, which is looking for additive functions of quantum channels. So in order to do that, I should remind you that any quantum channel that sends rho to rho prime in a noisy fashion, I can always think of as having this isometric extension to a unitary interaction with some inaccessible environment. And we're going to be interested in evaluating functions of a channel that are of the form down here below. I have some function of the channel n that also depends on some reference state phi that has a number of subsystems, v1 through vn, in addition to the input to my channel A. Okay? And then the function of the channel is just a maximization of one of these functions of channel n state over all possible states. And probably, if you want to be fussy, I should have said inf, because I'm not going to give you a bound on the cardinality of these states. So technically, wherever it says max, maybe you should think inf. And my goal is to, in a limited way, find all of the additive functions of this sort. I want to add another restriction, which is natural, given what I mentioned about entropies in information theoretic contexts. I want to look at functions of state, of channel and state, that are just linear combinations of the entropies of different collections of subsystems of this state. And where I mean the state being the thing that you make by feeding the A system into your channel to get some row V1 up to Vn BE. So now this is a sum over all the possible subsystems or collections of subsystems of V1 through Vn up and BE. And I have some coefficient in front of each entropy of the subsystem. And then the functions we're looking at are just going to be the maximization over all input states of such linear combinations. We want to understand when are such functions additive. And basically, all additivity proofs that you're going to find do the following. You find some state, phi, that evaluates, that gives a given value of this, this f of n and phi on two different channel uses. So I have n tensor m, the two channels used together with some reference state that has an input for each of the channels. And you take that input state and you find some way to break it up into two separate states, each of which only only gets fed into a single copy of the channel. So phi 1, say, would be acted on only by n, and phi 2 would be acted on only by m. And then you apply something like strong subadditivity in order to show that the function is subadditive. And furthermore, you can show it's additive from this as long as the function evaluates, as long as the function is additive on tensor product states, which all such entropy functions are. Okay? And so our goal is going to be not to classify all additive functions, but to classify all of these additive entropic formulas that can be shown to be additive in this way, and we'll call them uniformly additive. Basically, the additional assumption in this uniformly additive is that we don't get any special access to information about the optimal input state. We need this inequality to be satisfied for all states phi rather than simply the optimal state phi. Okay, so given that background, what we're going to try to do, well, what I want to show you is a solution to the problem. Okay, so we have a characterization of all uniformly additive entropic functions. This table basically collects all the information you need in order to write them down. And the goal for the rest of the talk is to explain what this table means and how to get it. Okay, so the canonical example of an additive capacity in quantum information theory is the entanglement assisted capacity. It's just given by this maximum mutual information between sender and receiver, and it's actually, well, it's additive like this, and you can see it has some kind of resemblance to the usual classical capacity of a classical channel. And I don't think it's actually a coincidence. I'll say more about that later. So how do we show that this thing is additive? Well, what you do is usually when you're trying to prove additivity is you kind of shuffle around all of your entropies and you hope that you can get your expression into a form so that then you can apply an entropy inequality like this one here that just says that this term, the mutual information, is always positive, so we can drop it. And if you've chosen the right form, generally you can show this additivity. So now we have this upper bound on the mutual, on this joint capacity, which is just the sum of the individual capacities, and we can achieve by using product state inputs. So this proof of additivity actually follows, well, has these two key steps. You can see first it takes the input state that we started with and splits it up into two different input states. One of them you get by just doing a trace over the A2 system, the input to the second use of the channel. And the other you do something slightly different. You apply the first channel and then trace out part of it. And then you leave the A2 system sitting around in order to be fed into the other use of the channel. So you can see there's something slightly non-trivial about how you pick this decoupling. And actually, that's going to be, the different ways of picking this decoupling are going to correspond to the different rows in the chart that I showed you earlier. And the second step, of course, is to apply some entropy inequality. In this case, it's positivity of mutual information. So the kinds of decouplings that we're going to look at are I'll call them standard decouplings. Basically, the trick is if I have some input state, phi, I want to find a way to generate an input, a state that, I can feed into, say, just a single use of the channel rather than two uses of the channel. And to do that, what you do is, well, you have to figure out something to do with this A2. You've got to get rid of it. What you do is you apply the channel that was supposed to be applied to A2, but you use these systems here as part of the reference state for the A1 channel or the N1 channel. Okay, so you make your new V out of both the old V and some choice of B2 and E2. And in a similar way, to generate phi hat, the thing that you feed into the second use of the channel, you just apply the first channel and make a selection from the subsystems of V, B2, and E2. Okay, so I've described the decouplings we're going to be looking at. Now let's talk about entropy inequalities. Well, actually, I mentioned strong subadditivity before. It's just positivity of this conditional mutual information. You can rewrite it by purification just like this. Actually, there might be more entropy inequalities. There are in the classical setting, but we don't actually know of any in the quantum setting. And you can express these entropy inequalities in a nice way. This is the set of, in terms of a cone. So what you do is you write down a vector that contains all of the entropies of the subsets or different choices of subsets of your or subsystems of your state. So if you have n systems, A1 through AN, you get 2 to the n minus 1 different entropies, and you say that it's realizable if there's some state that gives you a vector with those values of entropies. So not all vectors can be realized because there's some constraints. There's some relationships between the different entropies. But, and in fact, in fact, as you can see here in the two-party system, the set of allowed vectors actually forms a cone. Okay, so the cone is bounded by various planes that are defined by strong subadditivity, and actually we can use linear programming to test whether a particular entropy vector or candidate entropy inequality is satisfied. At least can be shown to be satisfied using strong subadditivity. And as I said, in the classical setting, there are these non-Shannon inequalities, but for quantum entropies, we don't know if there are any, though I think most people think there would be. Okay, let's talk about what to do if you're interested in characterizing these uniformly additive functions. Well, first, what you do is you write down the function you're interested in. It's sort of an arbitrary combination of entropies. And you have to fix one of these standard decouplings. Okay? So what you do is you fix some choice of how to map A1 to B1 and E1, and A2 to B2 and E2. And then you just write down what the thing is that needs to be positive in order to show additivity. It's just the difference between the sum of the two single-letter formulas and the two-letter formula here. And you need to find all of the alphas, all of the choices of coefficients that make this thing positive for all channels and for all states. And as I said, this also forms a cone, the cone of additivity for that particular standard decoupling. So as an example, let's look at the case where we have 0 auxiliary variables. That is where this formula doesn't have any v's in it. The formula only depends on the entropy of B and the entropy of E. So in that case, we have 3 terms, the entropy of B, E, and the joint entropy of BE. And in that case, the standard decoupling is actually very simple. There's only one. And it's just the thing that you get by doing partial traces, by discarding one system or the other. And if you write down this delta, the thing that needs to be positive to show additivity, it has a very nice form in terms of mutual informations. And then you have to ask yourself, well, when is this delta positive? And there are 2 ways to describe that situation when delta is positive. You can, as I said, there's this cone of additivity, and you can describe a cone in 2 ways, either in terms of rays of the cone, so that every point inside the cone is a positive linear combination of these extremal rays, which you can see on the left, or you can describe it in terms of faces, which is a bunch of linear inequalities that are satisfied by the coefficients of these entropies. And these 2 descriptions are useful in different situations. So what we know in this 0 auxiliary variable case is that anything inside this cone is uniformly additive, and anything outside the cone is actually not. So specifically, there will be a state and a channel that ensures that your delta goes negative. And the way that you do that is basically you find some particular state that singles out each of the linear combinations associated with a face, and that particular distribution makes sure that your delta needs to be equal to the thing that's constrained to be positive. So you can see that if you violated that inequality, you would also violate this uniform additivity condition. So for one auxiliary variable, where you now have some V system also running around, it turns out it's enough to consider just functions of this form that where each term involves a V. So there are now 4 coefficients, and now you have to fix a standard decoupling, which is just a way of choosing your V tilde on your phi tilde, which chooses basically either, well, one of these 4 options. V tilde can either be V, B2V, E2V, or B2, E2V. You have to do a similar thing for V hat, and this leaves actually 16 options for your different standard decouplings. Then you can define a delta that needs to be positive to show additivity of this function at the top. And you can ask yourself, what's the additive cone for this particular decoupling? Okay? And that's what this table tells us. There are actually only 5 inequivalent choices of standard decouplings. And for each of those, we've written down 2 descriptions of the cone and the extremal rays. And a lot of these things will look familiar to you. So this thing is sometimes called reverse coherent information. And you can actually build up the usual mutual information out of this, out of this table too. So in general, if you have one auxiliary variable, I said it was enough to consider this f of the particular form, that depended only, that had terms only with V entropies involved. But actually, in general, you need to find, the most general function with one auxiliary variable that's uniformly additive is a sum of a function with 0 auxiliary variables that's uniformly additive, and one of those special functions that I described on the previous slide. Okay? So what you have to do is put together the 0 auxiliary variable case and the 1 auxiliary variable analysis, and that gives you the most general 1 auxiliary variable uniformly additive function. And you can do the same thing for many auxiliary variables. You actually get to use the same table. You just have to sort of read off. Different functions for different decouplings that are consistent in some way. Okay, so this also gets us a list of all the uniformly additive functions with multiple auxiliary variables. Okay, and now what I'd like to do is take a closer look at one part of this table, and it's down here in the corner. So it's with this decoupling. We labeled it the 1-2 decoupling, and it's this quantity right here. We'll call it the completely coherent information. Actually, it's a new quantity. It's additive, which is nice. We call it the completely coherent information because if you got rid of these V's in the formula, it just would be the coherent information. So kind of by analogy with complete positivity versus regular positivity, when you add on some auxiliary variable to your formula, this formula becomes much nicer. So coherent information is not additive, but this completely coherent information is additive. It gains some unusual, well, some different properties from the coherent information. Particularly, it's symmetric in exchanging B and E. You could see that basically by purifying this formula. It's optimized certainly on a mixed state in general. It's a lower bound for the cost of swapping B and E, which is kind of intriguing. We hope perhaps it's even equal to the cost of the communication cost of swapping B and E. It's also an upper bound for the simultaneous quantum communication rates that you can achieve to both B and E. And we can show for degradable channels, which is a particular simple kind of quantum channel where you can evaluate the quantum capacity, it's actually equal to the quantum capacity in that case. And what we'd love to get is a cardinality bound on V, a result that says, when I do this optimization, I only have to look at states with some fixed dimension on this V, because a priori, that V could go off to infinity. The value of the function can't, but it may be that the optimizing state goes off to infinity. So actually, it's possible to substantially generalize this formula and write down a bunch of additive quantities. So we can actually replace the entropies in this completely coherent information with any function j that's additive on tensor products. And just this function will now be additive in general on different channels. And if j is monotonic under completely positive maps, it also turns out that the optimal state will have a trivial V, so a zero-dimensional V, if the channel that you're looking at is degradable. So for example, this J could be a Renyi entropy, a sandwiched entropy, or one of these alpha Z entropies as long as it's got the right values of alpha and Z. And this quantity here will give you all the nice properties that we got in the von Neumann entropy case. Oh, good. There's also a connection between this completely coherent information and something called the symmetric side channel assisted capacity, which is a nice upper bound for the quantum capacity. And actually, you can see that it's operationally just the capacity of your channel when it has access to some zero capacity assistance channel. And it's also additive, but even better, it's sort of the cousin of this completely coherent information. It's just the sum of the two different completely coherent informations where you've sort of reversed the sign. I should have mentioned earlier that this completely coherent information, you can actually, this function f of n and the state is additive, but so is it's negative. Well, so is -1 times that function. Okay, so by combining those two additive functions in this cute way, you end up with something that we'd actually seen before, this symmetric side channel assisted capacity. And actually, I should have mentioned that everything that we know of that's additive in the quantum setting, you can find on this list of uniformly additive functions. Okay, I just have one or two more things to say about this. Something that's really, I think, intriguing is that you can do this whole game for classical entropic functions formulas too. Now, I mentioned that classical entropies have a different entropy cone from the quantum things. So specifically, conditional entropy is positive classically, but in general is not positive. So if you have an entangled state, it can go negative in the quantum case. But if you run this whole game and ask what are the uniformly additive classical functions, you get exactly the same list as we got in the quantum case. Basically, it's because when you try to show this uniform additivity, you only use strong subadditivity. You never seem to get any benefit from using the positivity of this conditional entropy. And that's related to the fact that, or the observation I made towards the beginning, which was that the entanglement assisted classical capacity formula superficially looks just like the classical capacity formula from Shannon's original paper. Okay, and maybe, well, this is pointing, I think, to a more general kind of dictionary that maybe we'll be able to build between classical formulas and quantum formulas, and maybe even classical protocols and quantum protocols in understanding, well, that could come from at least uniformly additive functions. Okay, there are several, I think, interesting directions to go with this. The first is, well, the first thing I want to point out that classically there actually are additive functions that are not uniformly additive. So if you look at the minimum output entropy of a classical channel, this is certainly additive, and it's certainly not uniformly additive. What do I mean by that? I mean that if you look at the entropy inequality that you have to use to show additivity of minimum output entropy classically, it's not satisfied in general. It's only satisfied for the optimal state for that minimization. So specifically, when you look at minimum output entropy, you know the state's going to be pure. For a classical pure state, you know it's going to be a product state. So for minimum output entropy, the optimal state is going to be just after you apply the channels, it's going to be a product state again. So the entropy on a product state is just additive. It's equal to the sum of the individual entropies. But in general, you don't have that additivity. The entropy of a joint system is not typically equal to the sum of the individual entropies of the system. And that also points, I mean, the places where additivity is different between classical and quantum. Sorry, what happens in the quantum setting is sort of clearly quite different, right? Because if you look at minimum output entropy, we know it's not additive. And that argument I just made, it tells us that the optimal state needs to be pure, but we no longer know when the optimal state is pure that it's a product state. Indeed, it's not. And that means that we get this difference in which formulas are additive classically and quantumly. We suspect that actually for uniform additivity, how do I put it? Well, actually, I would like to know whether there exist examples of additive functions that are additive in the quantum setting that are not uniformly additive. We don't actually know of any of those at the moment. We've also been able to use this kind of linear programming formalism to study entropy inequalities in order to get some new single-letter entropic constraints on a channel that imply additivity of coherent information, something that generalizes the notion of degradability we call informationally degradable channels. And we have a suspicion that actually this is the only entropic constraint on a channel that will imply positivity or additivity of coherent information. And all of this stuff can also apply to rate regions of multi-user information theory in the classical and in the quantum setting. And I think a really interesting thing to add would be looking at formulas that have a constraint on the states that we're optimizing over, because often that kind of a formula does pop up in applications, especially classically. Okay, so this is kind of a summary of the talk. Additivity simplifies our lives, but actually it's quite rare in the quantum world. A typical additivity proof has two steps. You sort of decouple your bipartite reference state, and then you apply some entropy inequalities. And uniform additivity is sort of a formalization of this notion of a standard additivity proof, where you fix a standard decoupling, and then you ask what all of the entropy inequalities imply. We were able to classify all of these uniformly additive formulas, and it gave a nice new quantity called the completely coherent information that has, I think, some quite interesting properties. There are several open questions. First, there are two kinds of constrained additive formulas we could look for. constraints on the channel that imply additivity, or doing optimizations for all channels, but with constraints on the state. This completely coherent information, I'd love to find an operational meaning or a cardinality bound. I'd like to know whether it's convex. And even more, I'd like to understand this classical quantum correspondence and understand whether it's a coincidence or really means something about the relationship between classical and quantum protocols. And finally, I'd like to be able to apply this to formulas with CQ states at the input, like Holovo information or private information. We can do that by imposing new entropy constraints, but also it's a little bit unclear how to do the decoupling, because we need to find a way to do the decoupling that preserves the CQ property of the states. And with that, I'll say thank you.
Thank you, Graeme. So we have time for questions. So I wanted to ask, can you get something when you specialize to some specific class of channels? I mean, can you use this formalism and specialize it to nice classes of channels?
So it works best if the class of channel that you're interested in can be expressed neatly in terms of also linear combinations of entropies. So for example, if you like degradable channels, then instead of considering degradable channels, you should consider all channels that have that always have more mutual information between reference and output than reference and complement. And such channels, then you can throw in to your analysis and see which formulas become additive in that case.
Yeah, question?
Yes, did you say you could use it for the various Renier entropies or not? I got mixed up on that.
Oh, sorry. Well, what I said was that you can take this completely coherent information and make a function out of various Renier entropies or whatever squished entropies you like, and it'll still have the same additivity. The general formalism, I don't think you can. Actually, I don't remember. Is strong subadditivity satisfied by all Renier entropies? Someone knows that.
Well,
I think it's not.
The other thing I was going to say, which I've said to you privately before, is that the reason that the entanglement assisted capacity is given by the same formula as Shannon's capacity is that what Shannon discovered without realizing it was the formula for the entanglement assisted capacity of a classical channel.
Yeah. But what we should try to do is find a way to make more provocative statements just like that one by understanding this correspondence better.
I think that there's probably using the cones and the linear programming and so on a finite number of outrageous statements that you can make.
Okay.
So does it also apply for the squash entanglement of a quantum channel by Takeoki, Guha, and Wilde?
So
it looks like from what you said, but I'm not completely sure.
Well, you have to slightly generalize this because in that case you have a minimization and a maximization, right? Because we were just looking at formulas that maximize over one state. But if you now look at formulas that maximize and then minimize, then that falls out too. So actually the squashed entanglement thing that falls out here in the table basically is the squashed entanglement between B and E. Right? So, and because it's a maximization, it actually ends up being minus the conditional mutual information that you maximize.
Okay, I think we have to move on. So let's thank Graeme again.